So yeah, great. Let's get started then. Thanks everyone for taking the time. So the topic was the backfile logging and replication, as I guess everyone saw the things about it. And basically it's just to talk about the approach, share any concerns, and possibly see if we have some ways forward with those. And with that said, did you have time to read the approach overall? Do we need to kind of go over it, or do we want to jump straight into the meat?
Let's maybe reiterate the proposal just for the recording.
Right, that's a good idea. So the original design for the Raft replication was basically the same as what we do in Prefect when a replica is outdated. Basically, we just run git fetch, do the outdated replica from the up-to-date replica. That approach has a problem where every time you fetch objects, Git has to compute the backfile of the missing objects. So this involves then doing connectivity checks, and that can take a long time in repositories with large amount of references. When it comes to Raft, that problem is a bit worse than it's maybe with Prefect, mostly because we are replicating a log, so everything has to be happening in order, and it could be that unrelated writes get blocked behind this backfile computation. Because if a preceding log entry is computing a backfile for a long time, we cannot commit the subsequent entries. And to avoid that problem, what we wanted to do is basically then move that backfile computation to happen ahead of time. So instead of trying to compute the backfiles when we are replicating the log entries, we are going to compute them ahead of time before we create a log entry in the first place. So in that case, the log entry committing is basically just transferring the backfile over to the and the log entry in general over to the secondaries, and once that's done, the log entry is committed. And this brings some new problems, which is basically that we need to guarantee that the backfiles apply everywhere. Whereas previously, git fetch would figure out what the replica specifically is missing. In this case, we are sending a backfile to every replica, so we need a given backfile to every replica. So what we need to guarantee is that the backfile applies everywhere, or otherwise we can easily end up with corrupted repositories. To do so, we basically would be computing the backfiles based on state of committed references, a snapshot of committed references. And this is based on the idea that we don't know what are the contents of the object database on the replicas, but we do know what are the state of the committed references. And from those committed references, we can determine which objects the replicas are guaranteed to have, because every object has to be present in the replica for it to have those references. The other sort of a problem that this brings to us is that Gitaly has some RPCs which might do arbitrary reference updates. So generally this would work well with pushes. Pushes always push the objects that would be needed to take the server from the given references to the pushed references. But we have some RPCs that don't actually push any objects, like, for example, write-ref, which basically just updates a reference to point to an arbitrary object. The problem with that is that if these objects have not been reachable from the committed references for a while, it could be that some replicas have pruned them and others haven't. So we can't guarantee that these objects are actually present on the replicas if we update and just reverse the point to them. So to avoid that problem, then what we would sort of need to do as well is to compute a backfile again based on the committed references. So even if the leader contains the object in the object database, if the object that we are updating a reference to point to, it's not reachable from the committed references, then we would need to compute the backfile and send that to the followers, regardless whether they have the objects or not. Downsides with that is that with this backfile logging approach in general is that there are going to be duplicate objects in the log. This I think is fairly small issue given it's a transitory state. But the bigger problem is that connectivity checks are fairly expensive compute-wise, which is why we also wanted to take them out from the committing step in the first place to avoid blocking on that compute. So that's the sort of flow we are getting to now. Some other benefits that this gives us is that if we do compute the backfiles based on references that we know that every replica has, that can allow us to accept writes on followers as well, because they know that the leader has these objects in the database if they have the object in the database, as long as the leader doesn't prune them away. And more so in the future, if we end up with multi-region setups, we can also accept writes on non-voting replicas. So we can really distribute the write load on a high number of nodes. So to solve the connectivity problem, connectivity check problem, basically with them taking a long time and a lot of compute, there are a few approaches. The most obvious one is to, I think, speed up the connectivity checks, because this benefits also pushes in general, not just this replication approach we're doing here, but pushes overall take quite a long time. And for example, if you push to GitLab, GitLab repo takes about 30 seconds, I guess. Some ways we can do that was basically that what Patrick proposed already back in the day, to only check the validity of the new objects that are being pushed. So we could basically trust that the objects in the object database are already fine, and we only check that the new objects actually connect to the existing objects and are fine. Another option also proposed was to ignore a large number of references that are unnecessary for the connectivity checks. So basically, we don't advertise most of the references we hold in the repos. For example, the GitLab repo has millions of keep around refs, which are completely internal. We don't expose them to the clients. So the clients will not base their backfile on those references. So then it's also pointless for us to check whether they connect to these references. So in these cases, for example, the gitlab.com repo, or was it GitLab repo? I don't remember which one I checked. I think I checked GitLab repo, but it contains something like 13,500 references in heads and tags, which is a lot less than the 5 million something references we hold in the keep around refs as well. So this could be used to speed up the connectivity checks in general. Going further, like where the problem, why we need to compute these backfiles for the arbitrary reference objects in the first place, is that we don't know the state of the object database on the replicas. So if we are not guaranteed that certain objects exist on the replica, we need to send it to them. Otherwise, we would need to block the committing and log entries replication, because we need to compute the backfile and send the objects that are missing. So we need to be certain that we always include all the objects needed. And the uncertainty mostly comes from garbage collection. So if we only apply write objects into the object database that have been actually committed, so they've gone through the log and committed on in a quorum, and then we apply the backfile to the repo. At this point, we know that every replica has received all the same objects at a certain log entry, which is not the case currently, because you can, for example, have a failed push that migrates objects to the object database but doesn't do reference updates. And if there are leader changes, you might get another failed push in another replica, which contains a different set of objects. Or, for example, if there are reference updates that make the certain references, certain objects unreachable, then again, we are sort of hitting the indeterminates in the garbage collection. If we, so there's like a two-part fix where we can stop computing backfiles for these arbitrary reference updates, which is that we need to ensure that only committed writes end up writing their objects into the object database. At that point, we are certain that all the objects in the object database exist on all of the replicas. And we would need to stop garbage collecting at this point. So at that point, that would be already fine. fine to so we don't have to compute the back files for the reference updates. But garbage collection is obviously very useful. So then the next step there would be to figure out if we can actually take over the garbage collection and make it run through the log as well. So for example, the leader runs garbage collection, logs the objects that should be removed, make sure that no new write refers to these objects while they're in the log, and all the followers basically delete also the same objects. I think I don't really have an obvious way how to do that in my mind. I think there's it's in the danger zone when it comes to races as well. But yeah, that's sort of the overview of the problem we are looking at and possible solutions with just the general speedups in the connectivity checks and trying to make the object database contents deterministic and basically make it so that we know the contents exactly at a given log offset. Yeah, that's the overall problem we are talking about here. Do you have any questions or observations regarding that?
I hear you talking about the log. Excuse me, I might not be fully up to date, but are we in the current design still intending to have all mutators to be sequential or on the leader only?
So the reference updates have to be sequential, but the writes themselves don't have to be. So you can, for example, still accept 2 pushes concurrently. You can still verify their connectivity of the objects concurrently. But at the point when they are about to make those reference updates and verify whether the reference updates apply, that's where we have to sequentialize them.
Okay, yeah, that makes sense, because I was like thinking if we're using a log, then we know the exact state of the repository, but that's not true. That's true for the references, but not for the objects. So that explains that part. And then you say like, and in some point we can distribute the rights as well to followers. I didn't follow why that would be the case.
So the followers are always lagging the leader. And the followers will always have only references that have been committed by the leader and the quorum in general. So if references have been committed and applied to the repository, at that point we are certain that all of the replicas have them, sort of, at least majority of them, so they will never go away. All of them have these references, so every object reachable from those references is guaranteed to be present on every replica. So then if you wanted to accept writes from a follower, so okay, let's go back to I guess the problem in general with the writes is rather the connectivity checks and such. That's the very heavy part. Replicating the objects themselves, like if you're just transferring bytes and references across, that's not very compute expensive. So what we can do is we can basically distribute the connectivity checks and the receiving of the objects to the followers, but they will still need to go through the leader to actually commit the reference changes and replicate the log entry to the others. And we can do this basically because we know that so let's say a follower is that receives a write coming in. So it can ask the leader, okay, what's your current log offset? Okay, leader says I'm at 50. So the follower waits until it's has received log entries until the 50th log entry. And at that point, the leader makes sure that it doesn't clean up log entry 50. So at this point, we know that every replica will still keep the certain log entry in place. And the follower can basically run the push against the references state of the references log entry 50. So the backfile will apply to every replica that still is holding references to the 50th log entry. So the follower can compute the backfile and do the connectivity checks. And to actually commit the write, they will then send it to the leader, who will just verify the references and replicate it further. So in essence, the leader is still the only node that is actually making the changes and saying which order it is and whatnot. But we can distribute the expensive compute across the nodes.
I'm a little confused at how we're ensuring that all the replicas will have the same amount of objects when you compute the pack file and stuff. Is that basically whenever you like do a push thing, is there like an internal reference that's created to kind of hold like a snapshot of the current state of the repository, or what's kind of going on there? I guess I'm a little confused.
Yeah, so the first idea is that if you have references to objects, a given object, you hold everything that object refers to, connects to, basically. Because Git is a graph, so if you point it to the tip of the graph, you are guaranteed to sort of hold the objects that are early in the graph. So from the committed references, which are everywhere, we know that basically every replica has these objects. So when it then comes to actually the internal references, every log entry that we apply, it could be that. Okay, let's start from the push. So basically, what push does is that the server advertises its references to the client. The client sees what these references are and computes a back file that brings the server from these certain references to the new tips that it wants to point them to. Basically, if all of the replicas have the same tips at a given time, then we are guaranteed that back file applies. Now, the problem is that if there is concurrently another write that, for example, deletes all these references, makes these unreachable. So then if the back file is not immediately applied since it's sitting in the log, then we can have a problem where there's a garbage collection, it ruins these other objects that, you know, the back file, the client just based on, depends on. And every time we basically update references and we still keep the log entries, we will, like, let's say we delete master ref, for example. Every time we apply such a log entry, we will also create another internal reference that holds the old tip of the master. So this ensures that even if we delete like references, we are still holding the objects that they pointed to in the past. And that then ensures that if we are calculating a back file on an older state of the references, the internal references still maintain the object references, so they don't get garbage collected before this back file is actually applied. And this, and then from there on, that works on a single node. But then, because all of the nodes are basically applying just the log, so if the log applies on one node, the same result basically gets everywhere. They will always create these internal references, so they always guarantee that they don't ruin the earlier reference entries. And the back file from the next log entry will still apply. There's some bookkeeping to be done there. So we need to basically know that if we compute a back file at log entry or log offset 50, we need to ensure that the preceding, like that this, we cannot prune anything after, like, we can't prune log entry 51 before this entry is actually applied, because otherwise we would be pruning the internal references that we were maintaining. So there's certainly some bookkeeping to be done, but basically it's the guarantees come from ensuring that every log entry keeps internal references to the previous state of the references, and then we record the snapshots, the log offset where we actually computed the back file, and then we need to maintain this in place until we have applied all of the back files that depend on this certain log offset. I'm not sure if that answered the question. It's a
I think that makes sense. So is basically every time there's gonna be like an update to a ref, or a ref being deleted or something like that, that action's going to result in an internal ref being stored in the log, and that's gonna be kept around at least until something that was depending on it gets completed. Okay, that makes sense.
Yeah, although the internal references, they will also be in the repository, because they need to be holding the objects in the repository. But yeah,
the log will ensure they get replicated to all of the replicas. Okay.
Yeah, because every time a replica updates a reference to another state, it will create an internal reference to the old state until that log entry gets dropped. And at that point, we also remove the internal references.
How does this work with loose objects which don't have references pointing to them?
they can also have references pointing to them. It's not really much of an issue. You can definitely have a reference that points to blob, for example.
But
Yeah,
if that
don't.
yes.
Yeah.
If that doesn't exist, that means we need to create this reference.
Yeah.
Yeah. So for loose objects, do you mean like loose objects that already exist in the database when you're creating a reference update, or that don't have any, that are not reachable from any other reference yet?
Could you repeat that? Sorry, I didn't get that.
So what's the concern with the loose references, loose objects exactly? Is it like the fact that they exist in the object database before we, like, they're unreachable from all other references by the time we create a reference to them, or otherwise I don't like, in general, like if they are reachable objects, I don't think there's like a difference really in how this works.
If there's a if it's reachable, it's no longer a problem. But if it's an unreachable loose object, and then a client sends a pack file which references that loose object, but one of them prunes that loose object before we create that internal reference.
Like even in that case, I don't think it makes a difference whether loose objects or packed objects, because they are still unreferenced, unreachable objects in the object database. But if that happens, that we are bringing objects, we are making them reachable again, and they were previously unreachable, then at that point we would have to compute that pack file and ensure that they are included in the pack file, because they could be pruned otherwise from some of the replicas. Oh, so you just said that the pack file that the client sends could actually reference an unreachable object. If you refer to git push, this is actually not possible because of the reachability check that is happening in Git itself, where it really only considers reachable objects as existing, and the unreachable ones are completely ignored by the git push.
Ah, okay, that makes sense. Thanks. I didn't know that. Yeah, and also we need to do a bit more in that reference, like connectivity check as well, because like even if we get a push that contains objects that are reachable from some references, it's not enough for us, because we need to guarantee that they're not only reachable from the internal references we create, because otherwise it could be that there's a very internal references and backfiles based on them and accidentally, and then we prune log entries earlier and we can cause corruption again there. So we need to be able to ignore certain references in these connectivity checks that are being done for the pushed backs. So one of the things you said was that we could actually do the garbage collection on the replication log, and this avoids some of the problems. But I'm not sure whether this would actually solve anything, because ultimately the garbage collection is still very much dependent on timing, because it has to go to the on-disk objects and see when they have last been accessed. So this is still like kind of a distributed timing issue, I would say. And so I'm not really sure whether this is actually a viable solution. So, but I guess like the base idea there is that the garbage collection is okay. So if we only write objects into the object database that are guaranteed to be committed by the log entries everywhere, and then we know that the objects have been, every object in the object database has been made available to every other replica. So we know that the contents of the object database is equal at a given log offset between all of the replicas. And that removes one of the indeterminisms in the contents right now. And the other one is the garbage collection. So if we ignore garbage collection completely by just applying the pack files to the repository once it has been committed, the log entry that is holding it, we know that all of the replicas contain the same objects. And then further from there is the garbage collection thing that we would need to make it also deterministic. You could, and if you do it basically to make it deterministic, you would have to control it on the leader, because otherwise you can have timing issues on the other nodes again. So it would have to be that the leader goes through the objects, decides which can be removed, and sends that to basically through the log, commits it, and doesn't remove anything before it's committed, and then all replicas remove these entries.
John did have a proposal a few weeks ago for using cruft packs and just not deleting stuff. That would give a little more safety there at the cost of disk space, of course. That way we never really lose anything.
Yeah, this is also something I'm frequently thinking about, but I'm currently afraid that this is going to be a very tough sell to upper management because they have been so very, very strict about trying to reduce the disk space. If we now say we just stop deleting objects completely, then I'm not sure how well that would actually sit with them.
Yeah, I think that's the problem there is if we someone can push like 5 gig file and then not be able to delete it. It's not a great thing necessarily, but it would definitely make our life a lot easier because at that point we could actually know the contents of the object database everywhere.
Yeah, that's fair enough. I mean, you could still argue that it might actually be sufficient if we just give the user the ability to delete objects when they say so. Like that we never deleted them automatically, but only like when they know, okay, I've just like added credentials to the repository, or I just have pruned big objects, but they still remain, but now I want to delete them. If we only give them the ability to do that like manually, but don't do it automatically, then this might already be like a sufficient compromise.
Yeah, I mean, if we don't have to do garbage collection online, then it becomes a lot easier. You could have a manual button that says garbage collect. You lock the repository for writes. At that point, you can't have races. You delete the objects that you need to delete, and you ensure that the leader commits those deletions and the replicas just replicate, like follow up. Otherwise, you can have timing issues again on the in a distributed system. But yeah, if it doesn't have to be online, you can have like a stop the world garbage collection. That would certainly be possible.
The thing is that even if we do that, we still cannot guarantee that objects actually exist on all the replicas if they're not reachable at some point in time. For example, a client is perfectly fine to send over a pack file in a push that does contain objects which are not getting referenced by anything that is actually getting updated to. So they would be unreachable from the point where they actually arrive in the repository. And there's probably RPCs where we can actually demonstrate something like that too, where an object is being created, but is never actually made reachable by anything. And so we wouldn't ever get to the point where we replicate them. So
that should not be a problem if we only apply pack files that have been committed. Because if the client sends a pack file that contains extra objects, then we replicate that pack file everywhere, then all of the replicas will contain these unreachable objects. So yeah, but it needs to be basically, we need to change the right order of the pack files to basically first go through the log and only be applied once the log entry has been committed. And we should never write any objects into the object database that haven't gone through the log and been committed. Right now, that certainly would be the case because you can receive that pack file. You migrate these objects to the leader's object database, and later you git fetch to the followers, and you would not receive these. But that's a problem because we are sending sort of different objects to different followers, and the leader has more than. But if the pack files are the unit, and we apply the same pack files on every replica, then they would contain all of the objects.
I'm just a little bit afraid that we're like pushing Git a little bit too far here. If you say that we always control when objects actually land in the repository, that would mean that we have to always create manual staging or quarantine directories for every single Git operation, which we already mostly do. But there are still some exceptions, like for example, fetches are one of the big exceptions where we don't actually have this quarantine directory, where we probably could create one, but I'm just at times worried that we're maybe pushing this a little bit too far and like painting us into a corner eventually where we're not able to move out again because we make so many basic assumptions of how Git works.
Yeah, we're definitely taking a lot of stuff over here, and something we can't really do easily right now is to corrupt repositories through replication, which we can do if we screw this up. Yeah, it's definitely more complex. It's also more dangerous in this regard, but yeah, I'm not sure what's the if there's a viable alternative really. The thing is, like, if the replicas are not guaranteed to have the same objects, then you either have to do the object replica, like compute which object they're missing at the state when you're replicating, which then blocks the commits, or you do this what we're now proposing here and do it ahead of time, which means that you need to also do a lot more bookkeeping, which is somewhat more dangerous. but yeah, I'm not sure if there really is an alternative that we can do.
I mean, ultimately, this still stands and falls with being able to efficiently compute pack files, right? Because we've seen like the write refs RPC, for example, gets executed extremely frequently in busy repositories. And in that RPC, we're probably forced to compute pack files in some way or another. And so if we're not able to do that fast enough, then it would probably still like kill this whole proposal, right?
So yeah, I mean, if it completely saturates a Gitaly node every write ref, then that's bad, of course. It doesn't necessarily have to kill this because of the fact that we do have the option of doing something with the garbage collection. And if we do solve that indeterministic contents in the object database problem by only applying committed back files and ignore, for example, disabling garbage collection for now, then we don't have to compute the back files on write ref calls. We still need to do the connectivity checks on pushes, but we need to do them anyway. So there's no new, not necessarily any new connectivity checks that we need to do. The downside here is that with like that approach is that, okay, we lose access to garbage collection, but that's something that we can then further, I think, work on to figure out how to make it deterministic.
Also, wouldn't this mean that the Gitaly nodes actually have to have the exact same on this state, or otherwise this might fail?
Which exact on this state?
Like the pack files have to be one-to-one copy. They have to be exactly matching, because it can also be that we have inter pack file diffs, for example, of deltas when you have objects. So if one of the pack files does not match across the Gitalys, then the followers can easily get corrupted if they're not in one-to-one copy.
Well, if they apply the same back files and we never garbage collect any objects, then the content should be the same, right? That's the.
But the thing is, at some point in time, we have to like repack the pack files to make sure that a repository can be efficiently served to the client. There's just no way around this. I mean, we could do that and then just say, okay, we generate a whole new pack file and then we replicate that again, so that only the leaders actually doing repository maintenance. But if we do that, then we must also like always send over the pack file of all objects over the replication log, which means probably that in busy repositories we'll have a multiplicator of x times the repository size, because we have to store so many different pack files in there which contain all the objects.
So as far as I see, we should be able to repack and do all these things locally. It doesn't really make a difference here. The main thing is like the input of objects, like how do you get the objects in the first place, which means that we need to make sure that all of the same objects are going to all of the same to the replica. So if we take one pack file A and we just apply it on all, then we know that, okay, the objects are now the same in all of these replicas. And whether they repack or do things locally, that's completely fine, as long as they don't remove any objects.
But the thing is that the pack files depend on each other because of deltification. So if you repack all the pack files into a single pack file, then the other pack files that exist on followers wouldn't work anymore, right?
So I'm not actually sure. So the question is rather if we have the pack files in the log and we keep applying them one by one. So all of the replicas get the same pack files, and now one of them repacks. Will the pack file application from the log fail on the replica? Because it hasn't removed any objects, and it still has the same references, so it also needs to, if it doesn't remove any of the objects, it would still have the objects in the database that a given back file depends on.
I mean, applying the pack file should work, because if we're not creating a thin pack, then they're self-contained. I'm just talking about the scenario where we say that we don't do garbage collection, and thus also don't like repack on, or when you say don't do garbage collection, are you only talking about like not deleting objects, or also are you also talking about like not repacking the pack files?
Yeah, I'm actually only talking about pruning, to be clear. So
Okay.
all of the like everything else should be fine, but just removing objects is not fine, because that then causes indeterminism in the contents of the database.
Yeah, it's hard to say whether this would actually be something that we can do, because ultimately this is something we'll have to check with product team.
I mean, the stop the world garbage collection that you mentioned earlier, that's still possible, no? Because that keeps a consistent state on all followers, and we can still do that automated. It just is not it's not practical to do it very often.
Yeah, the stop the world garbage collection should,
I mean,
should be fairly like it should be completely possible, and we can then further iterate later on hoping to do online, but Patrick was saying so.
To be clear, I mean, stop the world garbage collection means that the repository cannot be accessed for half an hour plus for big repositories. That's not something that we can actually push on customers. At least not for the general case.
So another idea would be to run a garbage collection in two passes. One is that enumerates all the stuff that can be deleted, puts this in the log, and then this gets committed everywhere. But of course, this is racy by itself if you still allow new things to apply, but maybe we can check like from our own code whether there is an ongoing GC and whether it would delete some ref that that the new ongoing pushes are relying on. I don't know. But perhaps this could trade a slowdown. Like it would slow everything down because you have to do this while the garbage collection is running, but it would not stop the world. You can still make progress.
Yeah, so this sort of like garbage collection is probably the direction where I go, is basically that the leader collects the objects that can be garbage collected, then logs them, and once it's been committed, then it applies it everywhere actually. And during that time, the leader has to make sure that we don't paste backfiles on those objects. I think that would work, but yeah, we need to look further into that, because there are definitely like pitfalls there. But like just to say, like, okay, we don't have to compute backfiles if we do not garbage collect. Stop the world garbage collection would be fairly easy to add on here, I think. And stop the world means basically stop reference updates, not reads. But half an hour of no writes is still pretty bad.
Yeah, I don't think customers would be willing to accept that.
Yeah. Unless it's a manual step, but still not very good. And then the next thing would be to do this garbage collection in a manner that the leader decides which objects will be removed. And in the meanwhile, we guarantee that we make sure that we don't base anything on them. So like one of the ways to think about it is, I guess, that the garbage collection changes are only an optimization on top of the backfile. So you could technically do, like, while garbage collection is running, you compute backfiles for reference updates. And that also ensures that you have the backfile, like the backfiles contain the objects there. But the problem with that is that, of course, if the backfile computation is expensive and we actually want to avoid it, and that's why we would do the garbage collection changes, then, you know, you might just kill a server when it starts computing backfiles suddenly.
Yeah, it would probably also be very surprising to the customer if, like, every 2 hours, everything starts to become very slow.
Yeah, on second thought, I don't like the two operating modes, one operating like this and the other operating like that. I don't understand enough about the garbage collection to make a good technical arguments here, but it feels like somehow breaking up this big monolithic operation might help in some way. I don't know. I'll go and learn and think more about that.
I mean, sending over the objects that can be deleted should potentially be a viable solution to this. The question is, how fast can we actually evict objects from a repository? Like if the objects that are about to be deleted are part of the biggest pack file, then we still have to rewrite the whole pack file. And this, I mean, in this case, it probably has to be like kind of a stop the world scenario, because we cannot accept any writes while there is pending deletes of specific objects.
Is that
Well,
because receiving a new write relies on what is actually in the database?
I mean, it should, right? We shouldn't ever accept a write that starts to reference a object that we're currently trying to delete.
For pushes, that shouldn't happen because we don't really advertise the unreachable objects. But for these arbitrary reference updates, for these, it's completely possible that you could have. But then that comes down to concurrency control. So if the leader knows that it's about to delete some objects, that makes sure that there are no, just check that you are not updating references to this. So if you have a complete list of objects that are about to be deleted, just make sure that you don't allow reference updates or any, like you need to check that none of these objects are actually in the tree without being included in the backfile. Actually, you don't even have to do that because the backfile the client would contain the objects then again. But you need to make sure that the reference updates don't point to this about to be deleted objects.
But what I'm trying to say is, like, at the point where we decide that we need to prune an object, then we have kind of a write barrier, because it could happen that any subsequent write would potentially make any of the currently to be deleted objects reachable again. This means we cannot accept this write before we have deleted the objects. Or wait, it would probably contain the new objects in the pack file anyway.
If it's a push, yeah, it should, because it only advertises again reachable objects.
Yeah, if it's a write ref, then, and we don't actually do the pack file computation up front, then we still have the same problem, that we have to wait with the write ref update until the objects have been deleted.
I think it depends also, like in what kind of data we can get out of the garbage. So if we had actually, we get like a chain of objects that shows that, okay, these are reachable, you get a write ref. We know which write refs are already in the queue, in the log. So we can basically ignore those results from the garbage collection. And any subsequent process writes, we would just reject if they try to bring reachable objects again, reachable. It's a bit complex, but certainly it should be possible to synchronize this in a single process.
Wouldn't this mean, though, that we again have to do the connectivity check while there's garbage collection, because otherwise we cannot determine whether there is the about to be deleted objects become referenced again?
You have to do reachability checks if you don't have yeah, if you have an arbitrary reference update. The question is, you can't really. Yeah, I'm just wondering, like, it's most like, okay, can you have like how can you query that information efficiently? So if you know all of the objects that are about to be deleted, that's just a lookup, right? So if a reference is about to be pointed to one of those objects, it's just a lookup. The question is then, would there be any updates that could be pointing to some of the objects that are not to be deleted yet, but they would be referring to this? But that answer would be no, because Git wouldn't be able to delete these objects because there is another object that depends on them, right? So if you get a list of all the objects that are about to be deleted, then you just put them in a hash map and you can access it immediately and check if this points to any of them. Might be holes. I mean, I
delete 100,000 objects. Neither am I, so that's fair. The thing is that we quite frequently have the situation where there is hundreds of thousands of objects in a repository that are about to be deleted because they have become unreachable. Like, for example, today I had a look at the GitLab org/GitLab repository, and there were 450,000 objects pending deletion. If we have to check every single one of them, whether they might be referenced, then this check is going to take ages to compute. And then it basically boils down to the same old problem again of computing new objects that become reachable.
Isn't this a
So-
problem in like single node Git just the same?
Basically, well, it depends. Not really, because Git will verify when it's updating the reference, or when it's trying to update the reference. It first verifies whether the object exists, and when it does do that check, then it will automatically freshen the object so that it has an M time that is recent. And because of the M time, we know that this object cannot be pruned anymore. And thus the race window is about 2 weeks, and none of our updates for reference is taking more than 2 weeks.
Actually, I was occasionally wondering the same thing, because the garbage collection runs as a separate process, right? And where's the update race? So could there be sort of a time of check, time of use race actually there?
Not really. As I said, this is because of the race window we have. I mean, the shortest grace period we have is 30 minutes. So if you're able to compute the to finish the check before those 30 minutes, then you're good. Because as I said, when you update the reference, the object gets freshened, and then you have 30 minutes of time until the object may actually get deleted.
But rather, like, I'm thinking of the case where the garbage collection goes through the objects. It has identified a list of objects to delete, but hasn't yet deleted them. And now it figures out, okay, I'm going to remove them. And at that point, you have a reference update coming in. Well, I'm going to refreshen this up, and it should be safe. But if you already decided to delete, and between that decision that I'm going to delete this and actually deleting it, and you freshened it, is the garbage collection going to respect that? Or because somehow I'm not sure, like, I can come up with a model where you would synchronize that with two processes easily.
I think this issue should not exist, because the thing is that the garbage collection first explodes objects into loose objects, and then goes through them one by one. And I mean, yes, there certainly is a very brief race window, I think. So yeah, there's probably scenarios where the race can actually hit, and where we could make an object reference that doesn't exist anymore. Eber has also been talking about that when we have been in Chicago, about the case where there's a push ongoing that references objects that are about to be pruned, and this also is one of those scenarios where we can actually lose data and corrupt the repository.
Because like one of the, I think what I was also wondering that back in the day was basically like, how can we do it right now actually? Because like, okay, if we get like a direct reference update on prefect to such an object, it could be that actually the object that like gets lost even on the primary. So the question, and like, I guess traditionally Git servers only accept pushes, right? So then the question was sort of like, is the speed that we have in prefect actually, like, does it result like, okay, we have a lot of performance benefits from doing so, but like, do we have correctness issues because of doing so? And if we do have correctness issues there, then there's definitely a case that we need to do something there, I think. Either not garbage collect these things, or find a way to solve that race, or then compute the back files.
I'll go read the code again to see what's actually doing, and if it's actually possible to avoid this race in Git itself.
Yeah, thanks.
Anyway, this is all been talking about the case where we say that pack file computation is too expensive and that we cannot use it. This is still a question that is to be determined. I mean, right now I still am kind of pessimistic about this case, and I think that pre-computing pack files is likely going to be too expensive and that we cannot make it fast enough. like in GitLab or GitLab, it takes dozens of seconds, but I've also requested aid from SREs to give me a copy of this whole repository, including its pool, so that I can do some manual checks and local benchmarks to see whether it's actually possible to make this check or to make computing the pack file fast enough.
How realistic do you actually see to make it fast enough? Because on some level, like if we only check the connectivity of new objects to the existing references, that sounds like existing objects in the database. I guess that sounds it should be very fast. Like I think the results you had back in the day also showed it. And then the other aspect, like if we don't do connectivity checks with 5.5 million references, but rather only 13,000 references, do you think like that should already speed it up also quite a lot? Do you have an idea like how?
I'm of the opinion. First, I'm of the opinion that we should make it work with that we should always have a repository in mind that has millions of references. Yes, we can say that we exclude internal references and this make them less, but there's definitely going to be customers that have millions of references in their repository. So this is nothing that we can ignore. And with the current architecture for connectivity checks that exists in Git, I don't think we can make it work and make it fast enough, because ultimately the issue is still that when you have 1 million references, you have to load 1 million objects, and that's going to take time. And this is mostly the most expensive step of it, loading all the objects that are referenced by the references. But if we take the alternative and do what has been proposed by Taylor, where we have a bitmap in the repository that includes all currently reachable objects, then we can probably make it work fast enough. But this is going to take a long time until we arrive at that point in time, because we first have to do upstream work to actually make available such a bitmap. There's probably going to be a lot of discussion around it. So it's probably at least half a year until we have such a feature available. And even then, we still have to verify whether it's actually sufficient with regards to performance. I can probably give more information on how performant it is right now to actually do the connectivity checks with the tools we have available in Git at the current state. This should be, I can probably like provide those numbers by the end of this week. But anything else will we'll have to wait at least a few weeks to come up with a prototype to verify how fast it can actually be made if we use such a bitmap.
Yeah, I think that's fair. Like work-wise, it would be great to actually figure out what we need to then get in place to sort of try to parallelize most of the work. Yeah, I mean, to figure out the dependencies there, what we need to do. But I think in any case, like if we want to verify the logging approach, like we can verify the correctness and these things, write benchmarks and such already. And then eventually work on improving them or moving to the or doing changes with garbage collection, possibly.
We should, I mean, before actually doing something with garbage collection, we should definitely check with product before we actually start to do anything there, because it's a major change in our architecture.
Yeah, definitely. And also, like, we only need to change the garbage collection if we don't get the pack file computation fast enough. So I would also rather go that route first, because it also improves pushes. And if we don't get that fast enough, then we at least know that we have a way forward. But yeah, it's something that should be discussed in a larger context.
Yeah, one more point I had on my list is, in a world where we start to pre-compute the pack files and then make them part of the replication log, we will run into edge cases where the replication log becomes huge, because like, for example, if you push a whole repository onto GitLab, then there is potentially, the pack files are going to be like gigabytes in size, or even like hundreds of gigabytes in size for specific repositories. And thus it becomes a multiplicator in the size of of on-disk space you require for a certain repository, and we have to establish whether this is something that is acceptable or not. Like I'm to make my thoughts a little bit clearer, I'm mostly thinking about the case of huge mono repositories where there's customers which have only a single repository containing all of their source code, which is hundreds of gigabytes of size. Then they're probably going to provision the node hosting that repository with approximately like maybe twice that size. If they know, okay, I have 300 gigabytes of size of repository space normally, then I only have to provision maybe 500 gigabytes. But if we then start to potentially create a lot of pack files in the pack file log or in the write-ahead log, then they might have to start changing how they provision their nodes.
Yeah, that's definitely the case. Overall, ideally, in the ideal case, they want, of course, stay along in the log. It's as soon as they've been replicated to the followers, the backfiles can be pruned. If there's a follower that is down, then you might have to keep them longer. But then that's also a case of limits for us. Like, at what point do we stop keep holding those log entries and just drop them and then like replicate to the follower from a snapshot or like fetch? But yeah, I think that's, yeah, if they have such a large repository and they do want to make such large pushes, then I guess it's like you can ask them to also have a bit more working space available. If we actually make a case for it, but it's definitely something that, you know, the requirements are going to be increasing in this. We're on the dot, so does anyone have any remarks still to make, or should we conclude the meeting? Seems no. So then thank you for taking the time, and I'm going to stop the recording now.